Hello everybody. So in this video we're going to prove the fourth version of Hilbert's Nullstellensatz, which says the following. So we assume in this version, as we did in the second one, that K is an algebraically closed field, and we show that if I is a proper ideal of the polynomial ring in n variables over K, then this V of I is not the empty set, where this Vi is by definition, these are all the elements in the affine n space such that they kill every polynomial in I, right? So these are, if we call these closed subsets, one can show that they satisfy the axiom for topology. And this is the so-called Zariski topology on the affine n space, but we're not going to use this in this version at least. So before I move on to the proof, which is going to be quite short actually, I should make the following remark. So if K is, if I assume that K is an algebraically closed field, then by definition this means that every non-constant polynomial with coefficients in K in one variable is going to have at least one root in K. But it's pretty easy to see that this is exactly equivalent to the following fact, namely that if I is a proper ideal in the polynomial ring, then the V of that ideal, and I'm using the same definition, it's not going to be empty, right? In other words, the fourth version of Nullstellensatz is nothing more than just a generalization of this fact. Okay, so now we move on to the proof. Okay, so since I is a proper ideal, then we know from basic commutative algebra that we can find a maximal ideal of A such that I is contained in this maximal ideal. Now recall. Oops. So now we recall the second version, which said that we have this bijection between the affine n space and the set of all the maximal ideals of A, and it's given by sending a tuple alpha to this M alpha, which was by definition the ideal generated by this polynomial. So this is actually where I use the fact that K is algebraically closed, right? Since K is algebraically closed, I can apply the second version and get this bijection between the affine n space and the set of all the maximal ideals. So since we have this maximal ideal M, right, it's true using the surjectivity of H that we can find an alpha living inside the affine n space over K such that its image under H is going to be equal to M. So that is M is equal to this ideal. In other words, we get that I is contained in this ideal, right? And now I claim that this alpha is actually the element that lives in Vi. So in order to check that alpha lives in V of I, what we have to do is simply just take an arbitrary element f of I and show that f of alpha is equal to 0. But now this is really simple because, okay, let me just call this relation 1. So if f lives in I, then relation 1 implies that f lives inside this ideal, which I'm just going to call M alpha. But now this easily implies that f of alpha is going to be 0, right? So in other words, alpha lives in V of I, which is what we wanted. That is, V of I is not it's not the empty set. And this pretty much finishes the proof of the fourth version. So what remains to show is the fifth version of the Nullstellensatz, which is going to be the last. And but we won't do it here. We'll do it in the next video. So hope you enjoyed, and thank you for watching.